Now, let's very quickly talk about, because we started with the notion of swarm, so let's go on to multi robotics. There are two types. One is centralized. So this is sensor reading of robot 1, sensor of robot 2, sensors of robot 3, 4, all the way up to n. And this is actuators of robot 1, 2, 3, all the way up to n. So you had 3 robots. All of them give their sensor reading value on a communication channel on a central server. So all of them shoot all their sensor reading, all the sonars, all the light detectors, all the microphones, they all give it on one central server. That server takes all the sensor readings and tells what each and one of the robot needs to do on the actuator channel. So one system does everything up, and therefore it will behave exactly the same as always. So new evolution will remain the same. Fitness evaluation will be, instead of moving one robot, just move all the robots. And that's the beauty of centralized system. Everything is exactly same as one robot. It's just like one virtual robot has all the physical robots has multiple parts, and you're moving all parts together. So if I need to do a fitness evaluation under this setting, all that I'll do is I will take in my map with obstacles and with different robots, and each one of them will give the sensor reading value to a server which will calculate the actuator value, and then all of them will implement the actuator values, whatever comes out. But I cannot learn a swarm like this because the number of input parameters are now too many. Even for 3-4 robots, they are too many. And the number of actuator outputs, linear speed, angular speed, will also become too many. Even for 2-3 robots, it will become, for 3 robots, 6. There are too many outputs, too many inputs. So centralized is of course a terrible idea. Centralized is something that should not work, and that needs to be changed into a decentralized app. So let's take in decentralized. So let's take in the decentralized solution. Now the decentralized solution, it will come in two varieties. One is without direct communication, and the other is with direct communication. So let's take in a very simple example. I've got a map which is like this, and I have got a robot here, and I have got a robot here. Now there is a LED light over here, and the color code is, if red wants blue to follow, it turns it LED light as blue, and if red wants blue to stay away, it turns it as red. Two situations that they are searching for a common target. If the target is found, red tells blue you stay away because I found it up, you look for somewhere else. Follow because it's a long way, we need to continue working over there, or whatever be this thing. So in chaining we saw that the colors, the robots communicated by using lights. Light on means I'm the last robot attached to me, and light off means I'm not the last robot, so don't attach to me, don't move towards me. So that's without direct communication, or the communication happens only because one produces an effect and the other robot looks at that effect using its own sensors. So that's without direct communication. Now, things remain exactly the same. If you want to evolve this system, things remain exactly the same as a single robot. So here is your robot agent. You've got your sensors, say sonar, light detectors, and so on. And you've got the actuators as linear speed, angular speed, but now one thing which you'll also have is the LED light. Whether it should be off, whether it should be blue, whether it should be red. So that's an additional actuator. And what really will happen is that, let's say this is robot 1, and a replica of this is and it again has a sonar and a light detector. So if there happens to be that both of them are facing each other, there's no obstacle between them, then ideally this light detector, LED light, is being detected over here, and this LED light is being detected over here. So this becomes communication through LED lights if within visibility. And this could be any number of robots. It could be 3 robots, it could be 4 robots. The number of actuators are just 3: linear speed, angular speed, and the light communication control. The number of inputs are still the number of sensors plus one additional sensor, which is the light detector. The number of inputs does not increase, the number of outputs does not increase. You have 100 robots, 1,000 robots, a million robots, the number of inputs and outputs remains exactly the same. The only thing that changes is that communication channel, when you are doing the simulation, the robots will naturally be able to look at each other and will be able to decide what to do in the simulation. The good thing is, what needs to be communicated, nobody's deciding that. Red follow, blue not follow, nobody's deciding that. These are features which are calculated by the environment itself, by the learning itself. So it accidentally opens a red light and something happens. If it's good, it gets a reward. And then it learns that, okay, in this situation, turn your light on. It switches it off, something bad happens. In this situation, don't turn your light off. So the light controls or the light communication channel or light whatever needs to be communicated is what is seen by the different agents, what's learned by different agents as a part of the simulation itself. So that's something which is very good. In fact, even if I don't use light, sonar, so robots aggregating, using the sonars, they'll decide how good they are performing and how bad they are performing. That's the only thing that you can use in order to learn the behavior. So that's an example without the communication channel. Let's take in decentralized web communication. So this is like you have got a Wi-Fi network, you've got a dedicated Wi-Fi network, and because there's a dedicated Wi-Fi network in your lab where these robots are operating, all of them can communicate to each other, or one of them is, they're all wireless agents, they are connected to the same network, so they can share information. So again, it is the same sensors. I don't know why do I need light, but let's say it's to detect some kind of a goal, and the same actuators, linear speed and angular speed. This is robot 1. This time let's do it for many robots. And so on. Now what really happens is that they also get messages from the communication channel. So let's draw it a little bit separately. So these are messages from the communication channel. So anything that you broadcast will come in over here, and each one of them will will get it. And similarly, you can also broadcast the communication channel as actuators. So that's your normal actuators. And you also have an actuator, which is the communication channel broadcast. So theoretically speaking, Again, it's just that there was a communication channel that you could use to share any information possible. The only problem is I'm not programming them up, so I don't know what information to share. But there's a communication channel, and any robot can send any message. What message needs to be shared, what's the encoding, what's the format, everything will be learned. So neural network will try to give in some messages, and accidentally it sends a message to based on which some other robot reacts, and that happens to be good, then you can say there that's a good message. If you want, you can, of course, like a classification problem, say that these are 5 types of messages based on what you think may be important. Otherwise, it can also take in a continuous value. So the entire message format is also learned. One is a lot harder than the other as a learning problem. So you have a communication channel. Every robot reads from a communication channel. When you simulate it up, you just keep the communication channel on in your simulations. And once you keep the simulation channel or communication channel on in your simulations, all that happens is that whatever input comes, it's passed to neural network and it's processed as usual, as it would be. Whatever channel message comes, it's passed to the communication channel and it's processed. Whatever it be meaning, the neural network tries to make a sense of it. And if you want to publish anything, the robots keep publishing anything. If it's good, the fitness value will increase. If it's bad, the fitness value will reduce, and the evolution will happen so as to continuously, in an evolutionary framework, maximize the value of the fitness measure that has been set. Now, enough said, enough spoken. The practicality is single robot, multiple robots, whatever you do in your laptop configuration, the evolution and even in simulation will take in a very long time. It's different if you have a big computational facility where you can really do things in parallel. Even if you use a centralized computing facility with all its cluster, you'll have to learn how to program in parallel. It's not a normal programming. If you do it in your laptop, then it's still, the GPUs are not being used because your program will be completely linear. That means you're doing it on a processor, and on a processor it'll take a ridiculously long time. So practically it's still a problem. Practically you still need to say that, okay, it'll take a long time. And it's exactly the same with deep learning, of course. Today in deep learning, if you get the new data, you want to learn it, either you have high big GPUs, luckily we have at this institute, or you use Colab and these things, which you have a high compute power, and libraries which know how to use it. Otherwise, if you do it on a processor, it's extremely slow. Now, deep learning, of course, has facilitated from transfer learning or a pre-training. So you start from good features and then you only learn the difference and a whole lot of ideas over it. New evolution, you might actually want to do exactly the same thing, that maybe just program the behavior yourself. Maybe just write down a program yourself. Maybe just write down a behavior yourself. So we are using a lot of social potential field. Maybe just write it up. The problem with that model is human bias and lack of will to set good parameters on big test cases as in the initial condition only, and that's why the models are bad. Human bias, you will not test the program under different kinds of settings, easy to hard. You'll not test it with different parameter value. You'll not find out the best parameter value. You'll be very lazy, and your potential function rules will also be what you believe is good, which may not really work. So there's a big human bias around. So program it up, but that's not the best model. But what you can actually do is that you have a humanly designed model. Take this up, give random inputs, collect outputs, and you make in a table of inputs to outputs. I mean random as in you give in the real inputs in whatever you tested upon. So you get this input-output mapping. Use supervised learning. In fact, if the input is images, you can use pre-training and after that supervised learning. That gives you a quick-time model which is heavily biased by humans. But it gives you a model which performs good. So use social potential field for the obstacle avoidance behavior, for the goal-seeking behavior. Use it. Generate in a data set, so you don't need to do anything. You just need to write down a computer program that generates in a random map, puts a robot randomly in that map, and then let the potential field work for whatever time possible. Once a robot reaches the goal, you put it on another random location, let it reach. Once it reaches, put it on another random location, let it reach. Once it reaches, put it on another random point and let it reach. Once you're bored of it, load the third map, load the fourth map, load the fifth map. You've got too many maps. Let it run day and night. Every time as the robot is running, you are populating the database. So as a robot is running, you are populating this database. The inputs and outputs are getting populated in your simulation setup. This data table is getting populated and you're simultaneously learning that. So it's incremental learning. You also don't need to store it up. You can simultaneously learn it from a neural network. So a neural network is using artificial potential field to move the robot to make a training data set, and it's simultaneously learning from such a motion, from such an observation. And this function, because, supervised, it's a lot easier to learn. Subjected to the data, it's a lot easier to learn. You're getting a lot of data. So now you've got in neural evolution one neural network which does well. Now start the neural evolution part of it. So your starting point is good. Now you can do a normal neural evolution and try to reduce the bias, to try to let the network explore, but at least your starting point is good. At least you've got one supervised trained neural network. It has a heavy human bias in terms of design, but it's still good enough. So that's a good starting point, and you might actually start taking that up. Now, the other problem that really comes over here in neural evolution is similarly with the reinforcement learning, and that has got to do with the fitness function. So previously we used in a fitness function, let me see if I can quickly locate it up. Yeah, it's right here. So we use this fitness function. But then what are W1, W2, W3 and W4? Of course you'll use trial and error, but imagine every time you change W1, that entire big neural evolution is happening. You change W2, that entire big neural evolution is happening. It's not like a program which is taken milliseconds. Okay, so I try a lot of parameter values and I just look at it. Every time you change a parameter, the entire evolutionary robotics is running, and that's too slow. You don't have the luxury of doing that now, because every run of a neural evolution is something that's taking hours. So what you really do is there's another branch called as inverse reinforcement learning. So a reinforcement learning, the reward function is the input. So the reward function is always known, that's given, and the output is a model that maps the inputs to output such that that reward function is optimized. In inverse reinforcement learning, a model is the input. So you've got something that maps the inputs to outputs, which is like this neural network that we just now discussed. So the input is a learned model like this. It's something like this potential field, humanly designed. And the output is what will be a good reward function. Or in short, you try to learn a reward function, you try to learn the parameters of the fitness function using either humanly teleoperated trajectories or trajectories which are from this human designed model. And because it's humanly designed modeled, therefore it does have a bias, but it gives you interesting, good, strong W1, W2, W3, W4 to start off with. So W1, W2, W3, W4 can also be optimized. They can also be learned so as to make the model imitate what this potential field function or what this humanly designed model or what this teleoperated trajectories are the ones which come in as an output. So that's again a big field. So More importantly, now what we are saying is to really conclude this thing up that yes, neuroevolution does take in a huge amount of time, but you can make use of the fact that you already have good algorithms, you can use teleoperation, so you can have a good model that for an input produces a good output, and you can use it in multiple streams. One, to use it to generate a good initial training data so that your neuroevolutionary algorithms, your neural networks have good data to learn from, and second, to extract a reward function from it. Once you extract a reward function from it, you know what is a good reward function and what are good parameters of the reward function, so that you don't have that curse of changing the parameters per se. And of course, what we also can do is that because these are behaviors are naturally inspired, so you can also get the initial model by observing how humans move. So in our institute, we've got CCTV cameras. CCTV cameras monitor each one of you. So we learn how you aggregate. We call you in a field. We don't tell you why did we call, and we just see how are you coming, and we see how are you going back. CCTV cameras are observing you. So using that data, we find out how you are coming and going, and use that for either generation of the initial training data for the neuroevolution, or using that for making in a reward function. So a lot of research over there. The good thing is that these are real behaviors. So the way you behave is you're human, you're probably good. The bad thing is, of course, that the humans and the robots differ in one thing. The humans are almost non-holonomic. I can walk a square, I can take sharp turns, robots cannot do that. My speed is a lot higher than the robots. The humans have a lot more common sense than the robots. So the humans are kinematically different to robots. So I cannot always learn blindly from the humans and implement it on the robots, but it's a good starting point. It definitely has all the social conventions which are attached to it. So that's another rich data. It can be used to make a reward function, to make in the initial trained models for pre-training. These days, we also talk about virtual reality in the same framework. So we talk about virtual reality that says that instead of calling in you people now that the pandemic is just not ending, I can give you all headsets in a virtual world. So those VR headsets, and you move, and I can actually observe. The difference with the real one is that your behaviors in a virtual reality setup are a lot more synthetic. That's not how you would behave in real life, but they are still good indicator of how much distance you leave from the obstacles, how close you go from the obstacles. When you see people, how do you react to them? How do you avoid them? These are some things that I can definitely learn in order to extract a reward function or to train an initial model that will later on get more emphasized by using in a reinforcement learning framework. Of course, the natural data it's easy said than done. So if you really look at the CCTV camera footage, it's not high resolution. Extracting of the third component, they are 2D images, converting them into 3D is extremely noisy. And when you talk about things like teleoperation, the problem is there are humans involved and they charge quite a lot. And if we just call them for fun experiments, they give us random data. They just intentionally make the robot collide to the obstacle so that the work is not done. It doesn't pain to teleoperate a robot that collides. It pains when you hit an obstacle. So the concern is not the same, the behaviors are not the same, but of course it can always be used to generate in a good initial model as well. The best is to completely autonomous, use something like a potential field, a star plus potential field, navigation France, velocity obstacle. So these are established algorithms. They make the robot do interesting thing. They can be tuned up for interesting behavior. So you get a lot of data for free. the algorithms run day and night, and they make a robot move, and you are just logging on and making a machine learning system learn the model. So your recurrent neural networks are learning autonomously, your LSTMs are learning autonomously on this data, your potential field, velocity obstacle, probabilistic roadmap is generating a lot of data, and the LSTMs, the recurrent neural networks, are just learning this data as they go along. They both are doing it day and night. So you get extremely competent recurrent neural networks to start off with. Then you apply evolutionary robotics and simulation, and then you apply it on the hardware to just fine tune that model. These are the tricks which are just used to accelerate it up, to just get the results earlier. Of course, each one of them will have a heavy bias of the algorithm it's coming from. If it's coming from teleoperation, it will have a bias towards the operator who was operating it. If it's coming from potential field algorithm, probabilistic roadmap, it will have all the bias towards those methods. If it's coming from natural everyday scenario, then you need there's a bias in how humans operate, how robots operate, how humans operate are different because of the kinematics. If it's from virtual reality system, how you react is different. Even in virtual reality, you'll bang in obstacles and really enjoy it, so it has a very high bias towards that. So that's in short evolutionary robotics, wherein we use the power of evolutionary algorithms in order to autonomously make the robots program themselves, write their own codes in the form of a recurrent neural network, and they do something. They, if it works, those neural networks, those recurrent neural networks survive. If it does bad, they assess their own performance and they never repeat that. Those networks die in an evolutionary setup, and along with time you see more competent networks surviving, which better display, which better exhibit the necessary skills and traits that you were looking for in your robots, and they don't make the robots collide while doing what you wanted. That is the domain of evolutionary robotics.